Well, today we move on to Chapter 4. Chapter 4 is all about control volumes and especially how to use control volumes in open systems. So we will work on these open systems and address the equation of conservation of mass and the equation of conservation of energy on these open systems. That is today's lecture, Lecture 8. The rest of the chapter, which will go in 2 more lectures, we will describe to you a certain number of elementary machines that are based on the principle here of the conservation of mass and conservation of energy. These are essentially machines that will be the building block for the thermodynamic cycles that you will see later in chapters 8, 9, and 10. And there will be 2 lectures there, one where we'll describe nozzles, diffusers, turbines, compressor pumps, and one we will be describing heat exchangers, mixing chambers, and throttles. But let's start with the beginning, Lecture 8. So let's look at this essentially open system with an inlet and an outlet. But let's first look at what happens inside the system. So let's define the control volume as this dashed area here. We will be able to state, and the demonstration is in the next view graph, that the rate of change of the mass contained in that control volume is equal to the rate of change of the mass that flows into the outlet, into the inlet at time t, minus the rate of change of the mass that flows out of the outlet at time t, or eventually at an infinitesimally small increment of time after t. And so that expressing these words into a mathematical equation just means that the rate of change, the derivative of the mass in the control volume per unit time, is the mass dot, m dot in minus m dot out, or instead of having one inlet and one outlet, if you have n inlets and n outlets, you are going to make the sum over all the masses that come from the different inlets minus the sum of all the masses that come out of the outlets. So the reason we write this as differentials, I show in the next view graph. So let's just look at masses not in differential form. So if you have a certain amount of mass here in this other control volume, that moves into your control volume at a certain time t. So I have a starting mass at the control volume at the time t, and I add to that the mass of stuff that's in this little volume. Well, that is the same as the mass at that time t plus a little time interval afterwards, because this has to flow out, plus the mass that has flown out. Just writing conservation of masses at a given time t, or eventually a time increment delta t after time t. So basically what we're saying is what goes in must come out. That's what this equation says. Well, I can rearrange that equation and take this mCv of t, put it here with a minus sign, so I get this term, mCv of t plus dt minus mCv of t, and I rearrange these, me goes there, so I have mi minus me. I divide this by delta t, all 4 of these terms by delta t. That is mCv of t plus delta t minus mCv of t. In other words, this is the derivative of mCv per dt, and this is the rate of change of mass per delta t. That's m dot in, and that is m dot out. This is how we got to the previous equation. Now we're going to go a little bit more in detail in where these masses m sub I and m sub e came from. So here we're just going to consider a certain amount of area here in a cross-sectional area of the total area of a sample here. And we're going just to look at how many molecules impinge on this elemental area of the surface that we are studying. Well, the molecules that will impinge there over a certain amount of time dt are molecules that were within a length dt times, well, just dt times height, and they will all be the ones times the velocity, right? So a molecule that is here over a certain amount of time delta t will have the time to go from here through my cross-sectional area. But one that is here over interval dt will also be able to get through that cross-sectional area, and this height then simply is v dt. Well, what matters is actually the normal component of that velocity v of each of these particles vis-a-vis this surface area. So we can write this as for each element of surface area dt, we have a volume of cylinder that essentially empties itself through this cross-section will be Vn dt, or V dt time cosine alpha, where alpha is this angle. That's the volume. So this term here, dA V dt cos alpha, is the volume of this cylinder at a certain angle. And multiply this now by the density of the gas. That will give you the mass of gas that is in this gray volume, and that will empty itself through my elemental surface area here. So I just write here why that is, because Vn, the normal component, is V, the vector velocity here, times cos alpha. All right, so this tells us that the mass crossing this element of surface per unit time is rho Vn dA. Okay, so now we have to integrate this over all angles, alpha, and over the whole surface. So first of all, the m dot, so the rate of flow, will be the integral of rho Vn dA. This is an integral over surface. I denote double integral over A of a function dA is actually simply the integral of that function over dx, where x is one dimension, and that function over dy. This is simply an areal integral dA. So this is your expression for the change of mass, the rate of mass flow, per area dA is the integral over A of rho times the normal velocity times dA. So here we are again. Now, if we integrate that, and if the distribution of these velocities is uniform, and this velocity is unique, so there's only one value of v, and it is in the direction normal to the cross-sectional area dA, then I can solve this areal integral. In fact, rho doesn't depend on the area. Vn no longer depends on the area because I have given all the molecules the same velocity v, and I have told you that the distribution of velocity is uniform across an entire cross-section. So that comes out of the integral as well. And that just leaves the integral over the area of dA, which is the area itself, A. So here I come with this expression for the mass flow rate is the density of the gas, the velocity of the gas, the flow velocity of the air normal to the area of this cross-section of this tube times the area itself. Now, remember that we can write the density rho as 1 over the specific volume. So this very same equation, m dot, is area times velocity over specific volume. That means that I can write this for m sub I. This would be a sub I, v sub I over lowercase v sub I, specific volume, area of the exit pipe times the velocity, the flow velocity of the gas through the exit pipe, divided by the specific volume of the gas through the exit pipe. And now I can write my mass balance equation, which was dmcv dt is m dot I minus m dot E, as summation of a dot i's, v dot i's over v dot i's, a dot e's, v dot e's over v dot e's. This, of course, assumed that the velocity was uniform over the cross-sectional area and that all the molecules had the same drift velocity, the velocity v. The velocities are not always uniform, and that case will then be treated in your fluid dynamics class, not in our class. We will just assume that it is uniform, even though there is a little bit of an approximation. But for every exercise you will encounter, you assume it's uniform. Okay, So I can write my rate balance equation in discrete form, or I can write it in integral form. Discrete form is the one we just discussed before. The integral form is now the integral over the entire volume of my control volume of my density times my volume change. So I write a volume integral as a triple integral over volume. If you had x, y, and z, this notation of a function dv would simply be the integral of that function over dx, dy, or dz in Cartesian coordinates, or whatever other coordinate system you want to use. So that is one. And now we have the same integrals over the areas that I had before. The integral over the area that we had before for the exit, for the intake, and the volume integral for the control volume itself. That is the rate balance equation in a full integrated form. We had it in differential form before. So that was not too difficult to understand conceptually, but it walks you through the algebra. Now we're going to do something that is actually harder, which is going to go through the same algebra, but instead of with mass, with energy. And here it's going to be a little bit more difficult. So we have the same control volume here, and we're going to add heat to it or take work out of it. So the rate of change of the energy in my control volume is going to be the heat that I add to the system minus the work that they take out of the system. No surprise here, this is just the first law. But then there is energy that comes into my system because it's the energy that is associated with the mass of material at this inlet, and there's energy that leaves the system because there's energy associated with the mass of the material that leaves that outlet. Now, the specific energy in here is the internal energy of that gas, the kinetic energy, the velocity squared over 2, the potential energy, g times z sub 1. The same for the exit. We have the internal energy at the exit, we have the velocity at the exit, and we have the potential energy at the exit. So this is my rate of change. I had heat, work, and now I add to that this rate of change of the mass flow rate, in other words, times the energy associated with the mass that flows in, minus the mass flow rate of the stuff that comes out, times the rate of change of the energy that flows out. So essentially it's the same as far as the math goes. It's the same math as we had with mass, but with energy. We add two terms and we have these differential terms. Okay, so let's do this again and write it explicitly. So the change of energy in the control volume is the mass flow rate in, the energy in, mass flow rate out, energy out, or if you have multiple inlets, multiple outlets, it's just the sum of these things. Well, now comes a concept that's actually quite difficult. It's a concept of flow of work. So we are going to decompose the work that comes inside the control volume and in the inlet and outlet volumes, just like we did with the mass alone before, but now we're going to be doing it with the work. So we will say that all the work done on the control volume, whether it's electrical, mechanical, and whatnot, that is the work W dot on the control volume. Same with heat, we have seen this before. But now, the interesting one is the work that's done by the material that is leaving or entering the system. That, if you want, is the flow of work. Previous equation, we had the flow of energy, reasonably easy to define. The one before was the flow of mass, very easy to define. Here we have the flow of work, which is a little bit of a strange concept. Well, you know that the work is the integral of P dV, or in this case we have V defined. So we'll just say the work here that thing could do would be the pressure times the volume at the exit. Now, if we have a flow rate of work over a certain amount delta of time, delta t, then we can say that this is going to be, it's the same concept we had before with the flow rate through a cross-sectional area. It fills this little cylinder. So this is the area times the change in time times the velocity. All right, so because this is the volume of the cylinder, if you wish, of the work that comes out. So careful, this is volume and this is velocity. I have just decomposed volume into area times velocity times delta t. It's exactly the same thing that I did when I explained the impinging of the mass on the surface 2 few graphs ago. So it's the same concept we did here. It's this concept, but now applied to work. Let's go back. So that allows me to write this particular thing in work rate as pressure, area, and velocity. So this is work is pressure, area, velocity, time. The rate of the change of work is pressure, area, and velocity. I'll just take this and put the time down there in the denominator, and I get W dot. The same with the inlet of work, pressure at the inlet, area at the inlet, and the velocity at the inlet. All right? And now let's write an equation that looks exactly like the equation we had for mass or energy, but let's write it for work. The total change in work is going to be the change in work in the control volume plus the work, if you wish, that leaves pressure times area times velocity at the exit, pressure times area times velocity at the inlet. Now, recall that we have m dot to be the density times the velocity times the area, or the density, the area times the velocity divided by the specific volume. Plug that in, and you get W dot, is W dot in the CV. So this is the work on the open system. This is the work on the closed volume inside. And then we just substitute this here. So we have m dot P times specific velocity. Specific density, volume. Mass, pressure, specific volume. So the reason we do that is because it allows us to get rid of the velocity terms, which we couldn't possibly know necessarily every time. So now we have the change of rate of the work of the open system is the change of work of the control volume, mass, pressure, and specific volume of inlets and outlets. Let's rewrite this whole thing together. Change in energy per time is heat, work, and the energy that comes on the inlet, and the energy that's lost on the outlet. We have our work flow theorem, which we just described, which has the same form, except here we have mass times pressure times specific volumes. Plug that in, this in here, and regroup, which is what these two equations do. And you notice now that in the inlet, we have the concept of U plus PV. And at the outlet, we have the concept of U plus PV. This is why we defined enthalpy as U plus PV, so that we could rewrite this U plus PV as H. That is the entire trick behind the definition of enthalpy. That's why enthalpy is a practical unit. This is tabulated. This you have a hard time finding. This you have a hard time finding. This you have, well, so that is why we do it. It's just practical. So this leads us now to the practical rules that you're going to have to use when you treat a problem that is an open system. You will be able to, for the open system, write the change of energy as the heat in the control volume, the work in the control volume, which is different from the work in the open system. This is the control volume. And then the mass changes times the enthalpy changes here at the inlet and at the exit. For the closed system, notice you don't have to do this. You can have everything in terms of an internal energy only It's heat minus work. So the rule is that anytime you treat with an open system, you should work with enthalpy. Anytime you work with a closed system, you should work with internal energy. And this has to become a reflex. You have to memorize this. Open system, enthalpy, closed system, internal energy. That's just a consequence of this theorem, of this workflow theorem, and the definition of enthalpy. If you were interested in continuing thermodynamics at a more sophisticated level later, I will give you a little aside. We do this often in thermodynamics. We define a practical unit, a practical quantity that we can use in a particular class of problems. Enthalpy is a practical definition that we can use in open systems when we treat variations in pressures and volumes, which is what we do in most of the thermal machines that we will describe. People use thermodynamic in chemical systems to calculate thermodynamic chemical equilibrium. They actually define another practical unit of energy, which is the Gibbs free energy, which just simplifies their thermodynamic equations when they calculate chemical equilibrium, just like enthalpy simplifies your equations when you calculate a PV problem. And there is a number of these functions. We can define many others, the Helmholtz energy and whatever not. These practical equations are called the thermodynamic potentials. And for each definition of a thermodynamic potential, like Gibbs free energy, we actually have an equivalent of this workflow theorem that I gave you a minute ago. And these theorems then are called actually Legendre transforms, in case you ever encounter Legendre transforms. We're not going to go into this. You don't need to know this for 3501. But if you're interested, that is all part of statistical thermodynamics in 8502, which is a graduate level class, of course. Forget this if you're not interested in thermo. Listen to it, and maybe this will interest you in going to grad school. So we can summarize the whole thing once and for all. The change in mass, the change in mass is here. The mass at the given time t in the control volume is, of course, the integral over your control volume of its density times the volume. The change in energy is in the control volume. This is the energy in the control volume. This is the density to be integrated to the volume, of course. The change in mass with time at the entrance and the exit of your system is the integral over the areas of the inlets minus the integral of the areas of the outlets, all summed over all outlets and summed over all inlets. The internal energy then is heat, work in the control volume, and then the integrals essentially of the enthalpies, the kinetic energy and potential energy, inside all the inlets, integrate over the areas of the inlets, and the energies, the enthalpies, kinetic energies, and potential energies of the material that goes through the outlets. Now, if it's in steady state, that means that the derivatives with time are zero. So that means that there is no change in mass in the control volume, and that means there's no change in energy in the control volume. That just means that whatever comes in has to come out, which I express here, as far as mass goes. And it also means that the change in energy over time is zero, and I had to take that previous equation, heat, work on the control volume, and then work on the inlets and work on the outlets, enthalpy, kinetic energy, and potential energy. So if you have one inlet, one outlet, you can simplify that entire thing as this equation, which you can rewrite. We just regroup it. So we group it in heat per mass, in work per mass, or heat change per mass change, work change per mass change, and then the differences in the enthalpies in and out, because the mass in and the mass out is the same. If you have only one of them, mass in equals mass out in steady state. So we just call this mass. We regroup these mass ins and mass outs as mass, which we take out of the bracket. we have differences in energies, and we regroup these in differences in enthalpies, differences in kinetic energies, and differences in potential energies. That is really the equation that you will need to remember. Well, not quite remember, but you have to be able to look it up very quickly. It holds only at the boundaries of the control volume. Notice in the control volume, we have set things to be not changing at all. So it doesn't hold inside the control volume. It tells you nothing about what happens inside the control volume, but that's actually most of the time not exactly what matters. When you're going to be solving a problem, you're going to look at the energy change between the in and the outflow of material and of energy in a particular machine. So this is the equation that actually will matter, and we will study that equation in great detail in practical cases in the lectures that will follow. Let me summarize all of this. The use of the workflow theorem was so that we could define enthalpy and in such a way that enthalpy becomes a practical thermodynamic variable to be used in an open system. Whereas anytime you have a closed system, you're still going to use internal energy like we learned before. So piston cylinder assemblies have a variable volume, but they are essentially closed systems. So when you have a piston engine, you're going to be using internal energy, U. When, on the other hand, you have a turbine, which is an open system, you are going to be using enthalpy. And then to summarize, in steady state, when you have multiple inlets and multiple outlets, you have this here. If you have only one inlet and one outlet, what comes in must go out, so that means there is only one mass that you need to worry about. There's no change in energy in the control volume, which means that the balance of the heat change rate, the work change rate, and this mass has to be obeyed, and you can regroup this mass as a function of the change in enthalpies, the change in kinetic energies, and the changes in potential energies of the gas of mass, flow rate, and dot. If your system is not at steady state, it has transients, and then, of course, the mass in the control volume can change over time. What we're saying then is that the change of mass over control volume over time has to be the rate of mass in and out, the change in mass in and out. The same then with internal energy, which we express now again as far as the masses that go in and out as function of enthalpies, whereas this is internal energy, careful there. And the mass is the volume of the system divided by the specific volume, of course, so we can rewrite this in terms of mass and specific internal energy. And you can do the same with specific enthalpy here. We have done the same with specific enthalpy here. So that was my summary. All very theoretical. We have to get through this, and then we'll do examples in the next lecture. Thank you.